Welcome to the 2020 SDC talk on Samba logging architecture. My name is Volker Lendeke. I'm a member of the Samba team and I work for Zernet in Germany. And I've been working on this for quite a while already. And I would like to describe you how Samba implements all the SMB logging requirements that we have to implement under different requirements, and I will describe how all the layering that people need to know works when adapting Samba to different needs. So what is Samba doing? Samba implements the SMB protocol on top of Posix file APIs. SMB and Posix both define file access methods. SMB is a protocol defined mainly by Microsoft. Posix defines a local API. Protocols these days are understood as API as well. Look at the notion of a RESTful API. That is essentially a protocol. So the distinction between a protocol and a local API is not really there anymore. Both define files, directories, metadata, and how to deal with them. In both worlds, Posix and SMB, you can of course open, close, read and write. You can create, list and delete files. You can query metadata. You can set timestamps and all that stuff. So at a very high level, they are a bit similar. However, in the details, there's a lot of differences. One main one is case sensitivity. Posix distinguishes between two file names, test.txt and test.txt, that have different uppercase, lowercase combinations. Windows does not. Also, the semantics to delete a file are different. If you look at how Posix does it, there's a simple unlink syscall that just takes a file name and removes the file from the file system. SMB used to have, in very ancient times, used to have an unlink call as well. But these days, SMB clients open a file indicating the intention to delete it when closed, and then close the file. SMB also has the concept of file change notify, which means that the client can ask a server, please tell me for this and that directory if anything changes in that directory. And also, by the way, I want to know if anything below that directory changes. That's recursive file change notify. And that's really a challenge to implement. Posix doesn't have this. Linux has some APIs for this. What we use right now is, for example, iNotify, but iNotify is not really recursive. So we have to implement something on top in Samba. If you now look at logging semantics, they are vastly different. SMB by default has something called share modes, which is essentially a way to open a file in a mode so that nobody else can open the file concurrently. Posix would call this mandatory logging, I guess, but I haven't really seen a use of mandatory logging in the field yet, so I'm not sure if it's correctly implemented. It's definitely not so popular. Posix very much depends on advisory logging. So essentially in Posix, logging is more like a, hey, I want to have this exclusively. Please, everybody else also access this resource. Please also ask whether I am right now the owner. SMB is much different here. If you log a resource like a file or a byte range, another difference, then this resource is actually logged and other concurrent access, different concurrent access is blocked. The other thing is SMB is a protocol. It has to deal with file and metadata caching, and SMB does define a protocol to coordinate caches and guarantee cache coherency, and that's called leases. So Samba sits in the middle between SMB semantics coming in from the network, from clients, and has to implement this on top of a Posix file system. You've seen most of this already, I guess. I just want to reiterate a few pieces of Samba architecture. Samba is a pretty old daemon, so it has the architecture like former telnet daemons, for example. Every connection that comes in gets a new process. This means that every process dealing with a single client has a completely distinct memory space that no other process can directly access. If you now look at the documentation for the protocols that are laid out in the documents MSSMB2 and FSA, and of course others, they suggest a lot of shared tables. For example, lists of clients, lists of tree connects, which are share connections, lists of open files, and many, many other tables. Samba cannot use any of these data structures directly because the MSSMB2 and MSFSA essentially assume a shared memory space across all client connections. So what does Samba do? Samba stores these SMB2 and FSA tables and metadata in file-backed key value stores. Key value stores are pretty well known these days. It's not that we are talking a protocol here. I'll come to that later. Right now, we have a local database called ctdb, trivial database. It's something that others can use. It's LGPL, so other projects or other even proprietary products can use it in their code. You can find it under tdb.samba.org. And if you look there, TDB is a simple database API. It was inspired by the realization that in Samba we have several ad hoc bits of code that essentially implement small databases for sharing structures between parts of Samba. This is text. This has been written mid-90s, I would guess. I didn't really look it up, but it's ancient. What is TDB? How is it implemented? It's a shared hash table with hash chain locking. So what we have is we have a data structure, a 4 GB, at most 4 GB file, where you have a number of initial pointers to data, and it's a singly linked list of elements with a free list and so on. And to protect these data structures, you get hash chain locking. How did this all start? How and why was TDB developed? Long ago, Samba 1. something, Samba used for the same purpose System 5 shared memory, together with System 5 semaphores. This System 5 inter-process communication APIs haven't really taken off, and the ball settled on mmap and F control at that time. And as you could see in the little introductory text to TDB, essentially this is a library that abstracts away all the different implementations that used System 5 shared memory to just implement a little shared database. The API looks pretty simple. You have calls to get a record, to store a record, to delete a record. You have, of course, an API TDB traverse to list all records and so on. The difference that you have here in TDB, and that is going to be important in a few slides, is that normal key value stores, look at Redis, for example, you don't really have per record logs. TDB doesn't have either per record logs, but what TDB offers is a user space API called TDB chain log. What it does is it logs a complete hash chain. And I'll come to that later. I'll come to the problems that come with this a bit later. TDB has seen many extensions and optimizations over the years. At some point, somebody decided, hey, we need to have real stable data. So we added transactions using fsync and msync. Those are, of course, relatively small, but what can you do with fsync? And we have really done a lot of tuning in the past to optimize for the use cases that Samba has. And I would say that for the use cases Samba is not, Samba has, TDB is not really a performance bottleneck anymore. The data structures in TDB are still 32-bit. Yes, for some use cases this is a problem, but for the transient locking data that we have, this is good enough. For the reason of 32-bit mainly, the Active Directory domain controller that Samba implements switched to OpenLDAP's LMDB. That can do 64-bit, essentially arbitrarily large databases. And that's needed because Active Directory databases can become larger than 4 gigabytes. Okay, the first real extension that I would like to talk about that is reflected in the use of Samba's use of TDB was driven by the need to cluster TDB. What does it mean? TDB uses a local shared memory segment because it's fast. However, shared memory is of course not remotely accessible, not in general. I mean, you have RDMA, but that's not really easily remotely accessible. It's also with special APIs and so on. You need specialized hardware. If all you have is a IP network between your nodes in a cluster, shared memory is not remotely accessible. So what did we do? Where did we want to go? We wanted to have concurrent access to the same TDB database across a cluster. And for this, we initially needed to define the semantics that are required to implement what Samba uses. So TDB, of course, is modeled after what Samba uses, but it's not an exact match what we really need, because evolution of Samba has led to some patterns that we use or don't use anymore. So when we, in the late 90s, when we started to cluster TDB, or no, it's early 2000s, we started to cluster TDB. What we did is we put in a layer between this main Samba code and the real access to TDB. We called that dbwrap, the dbwrap API, and the main call that dbwrap implements is this dbwrap fetch locked. And this essentially covers what Samba really does. It's first a record lock, and it gives read-write access to the record contents. And so what you do a dbwrap fetch lock, and you need the handle. I'll show you that in the next slide. You need this handle to access the record's data. And as long as you keep this handle around, you will hold a lock on that record. And that's the API that we implemented. If you just want to read a record, we have added a dbwrap parse record that's unlocked read. For many use cases, this is enough. But if you want to modify a record, or if you want to do some operations under a lock, dbwrap fetch locked is what you need to do. We did it in a way that you can do a flexible implementation of dbwrap. The default that we initially did was local TDB, of course, because that's what we have. And to show that this actually works even with other implementations, we implemented dbwrap file, which does the following. It uses a shared directory between all processes, and per record that dbwrap has to manage, it uses one file per record. The name is a hash of the key. We have a key value store, so we have a key, we do a hash, and the hash is the file name. And what we did to initially prove that Samba can actually scale and run on a cluster file system is implement this and put these dbwrap file per record files on a shared file system. At that time, it was GPFS. This enabled us to then focus on something that Samba does it on its own. And we started this cluster TDB project, ctdb, which started also as a completely separate project. Right now, for a couple of years, it's merged in Samba. So this does not use, it still does the local API with TDB, but ctdb coordinates access to the record that dbwrap fetch locked needs to access. ctdb organizes pushing these records around in a cluster. ctdb is a completely separate topic that really justifies more complete talks, but clustering TDB, and this is the takeaway from this slide, triggered putting in this dbwrap layer around what Samba uses from TDB. So what does it look like? This is a short excerpt of the dbwrap API. And as I said, dbwrap fetch locked, the most important call. What does it take as arguments? It takes a DB context. And each of these databases that Samba uses, of course, gets a DB context. Then it takes a memory context. What is this? It's a talloc context. All of Samba essentially uses talloc, which is a hierarchical memory allocator based on top of malloc. But it is really, really a cool thing to do, just to attach a record or attach some memory to some other memory, and you can have a whole memory hierarchy under this mem context. And if you do a single talloc free on this mem context, everything below it goes away. So what does this mean? You do a dbwrap fetch locked, you give it a database, you give it a memory context, and you give it a key, which is essentially just a blob. It's a data blob. It's a pointer to a uint8 and a size, and that's the database key. And what do you get back is a pointer to a struct db record. And there's another, so what you have when you hold this pointer to the struct db record, you have a lock on the record that is indexed by key. And as long as this pointer is valid, this lock will be held. And if you then talloc free, so there is no dbwrap fetch unlock or something. What you do is you just do a general talloc free that might come in just via talloc free on this record. But even if you just talloc free the mem context that you pass in, the record will go away. So what can you do with this struct db record? You can get its value, you can store new data, you can delete the record. And that's basically it. Of course, as I said, you still have these traverse and so on, but that's the core API. You fetch a record. If it doesn't exist, it will get created once you do a record store. But if it doesn't exist, you get a record that represents what would be in that key, and you already get the lock for that non-existing key. Essentially, it's the chain lock for the whole hash chain. And yeah, so dbwrap fetch locked represent both data and the lock. As I said, it's talloc based, so talloc free unlocks the record implicitly. And the only way to access and modify the record data is via the functions acting on struct db record. I'll go back to the slide again. You see, if you say dbwrap record store, for example, it just takes the record, it takes the fresh data, and some flags like, hey, override or whatever, insert, which means, yeah, some TDB semantics. So the record store just takes the record that you got from fetch locked. Likewise for delete. So how is dbwrap fetch locked implemented? It's implemented as a function pointer inside a struct db context. In the last slide, you saw dbwrap fetch locked takes the db context. And what you can do as an implementer is you can just implement different function pointers inside the dbwrap database, dbwrap context database representation, and just do it on your own. Samba gives the promise to only access the database via these APIs. What does this mean? Other key value store implementations could implement those methods. And this already has happened. I believe that somebody has implemented the dbwrap API on top of Apache Zookeeper. And it should be relatively easy to implement this, for example, on top of etcd or something like that. Okay, so this dbwrap was the basis for clustering TDB. The next step was, hey, we need a good abstract API to look for record changes. Why is that? Okay, cache coherency. I spoke about cache coherency in one of my first slides. Samba implements these leases that coordinate cache coherency. What is a lease? It's a guarantee that the leaseholder has exclusive access to a file, which means if I as a client know that I'm the only one accessing this file in the whole system, nobody else cares about its contents, which means that I can do a lot in extensive caching of reads and writes because nobody else cares. As long as, for example, my application doesn't really do syncing, doesn't require syncing, I can just cache in the implementation of the SMB client all reads and writes. This is just a very bad and lossy abstraction, but for this talk, it's good enough. The point is that I can be told by the server, hey, somebody else wants to access this file concurrently. Please, client, give up your lease. How does this work in Samba? So look at the sequence of events. So client A opens a file, it gets a lease, which means that it has the exclusive right to do full caching. The corresponding SMBD, and remember Samba has a process per client, updates a database, a shared database, logging.tdb. So now client B comes in and also wants to open the file. There's a corresponding SMBD called lowercase b, looks at the logging.tdb entry and finds the lease being taken. What this means is that the process B needs to inform A, hey, please, SMBD A, ask your client, hey, give up the lease. That's a message sent from process B to process A. Process A gets this message, asks its client to give up the lease, the client gives up the lease, and then process A modifies login.tdb with the new contents, hey, I give up, my client has given up the lease. Now, how does A, the client who has just given up the lease, tell B about the lease state change? And what does B do in the meantime? And for this, we implemented a new API that's layered on top of dbwrap. Okay. SMBDA gets a message from B to break a lease. And one of the questions is, how can A now inform B when the lease is broken? We could have done this that SMBDA knows where this message comes from. SMBDA gets a message from B to break a lease. It knows the source of this request to break the lease. It could record this. Also, the problem here is what happens if more than one client wants to break this lease simultaneously. So there's a lot of burden on the implementation because there are race conditions and so on, messages, whatever, not being transmitted in the order that they were initiated and so on. There's a lot of maintenance work on the process holding the lease, in this case A, and that's tedious and error prone. What we did in a previous implementation, the lease breakers, in this case B, so the second one, trying to have the lease broken, they added themselves to the logging.tdb file metadata. And so a lease break will essentially be put down in the logging.tdb record, and process A will notice, hey, there is a waiter. And we abstracted away this, hey, let's add ourselves to the logging.tdb file metadata to watch for a record. So B asks A for, hey, I want to get informed when the lead is broken. This means I'm interested in any content change when the lease is broken of the record corresponding to that file. And this is the so-called dbwrap watch send API that abstracts away this, hey, let's add ourselves to the metadata. Let's see how this works. You have a dbwrap watch send function. What does it do? Again, in good tradition, it takes a memory context and it gets a event context. I'll get to that. As an argument, it gets a db record. So to watch a record for changes, we need to have a struct db record, which means, if you look back a few slides, which means we need a record log. So we need to be able to modify the record essentially. What it also takes is it's a blocker PID. Our struct server ID is essentially a cluster-wide PID, because all cases that we right now have, all cases in Samba that use this API use it because they are blocked by some other resource, and usually it's a process. So we can't really open the file when the lease is taken, so we have to wait for the lease to be released. But what happens, for example, if for some reason the process, in this case process A, is killed hard? This is also, of course, something where we could just continue, because then the file is closed by definition. And this is why we have this blocker that says, please please inform me when anything in the DB record that I handed in changes and when this process dies. So what does it do? Watching a record creates an asynchronous computation. And what you get back from this dbwrap watch send routine is a struct tEventRec. What is this? This is something that Samba has implemented, and languages like JavaScript or something, or Rust, or Rust would call this a future. I think JavaScript would call this a promise. Essentially, it's a representation of an asynchronous process that waits to be fulfilled at some point later. And this tEventRec is a promise that gets fulfilled when the record changes or the blocker dies. And this is implemented as part of tEvent. And if you look at tevent.samba.org, that's also a separate project that we forked or published separately under LGPL. It's usable, and it is actually used outside of Samba. And I had to write here, it makes async programming in C a lot of fun. And I can really say it's true. All we do in Samba right now is asynchronous, and it's manageable. So it's really event-driven programming in C, which you can actually handle and manage. As I said, blocker is a PID that holds the current resource we are waiting for. In this case, it's process A. And if that dies, also the tEventRec also fires and is fulfilled. How is this implemented? It's layered on top of any dbwrap implementation. So you have one of these databases that's represented by a dbwrap context, or db context, sorry. And you can say, okay, I put a layer on top that says dbopenwatched. What does it take? It takes a messaging context. That's a representation of, as it says, Samba internal interprocess messaging. You can use this messaging context to send messages to fellow SMBDs, to any process that's in the Samba world. What does it do? It enables watching records on any lower level key value store implemented by this DB context. And when using such a watched database, this list of watchers is added to each record. So what dbopenwatch does is it just redirects the function pointers for fetch locked, for get value, for dbwrap store. It just redirects these function pointers to its own implementation, adding its own metadata in a single file. The API users of the DB context that dbopenwatch returns still use the dbwrap fetch locked API and friends as they did before without this. However, this is a database that you now can use to pass in to this dbwrap watch send API. You can't do this dbwrap watch send to an arbitrary database. You have to have this as the return of dbopenwatched. What happens when you now do a dbwrap record store on such a record? It will just ping all watches to fulfill this promise returned by dbwrap watch send. Okay, now to answer these oplock questions. So when asking for a lease break, the breaking process B watches login.tdb record when it finds when it finds a lease being granted. So how does A tell B about the lease state change? It just does a dbwrap store, record store. And because this database is being watched, this store triggers implicit messages to the process waiting for the lease break. So the dbwrap watch code takes care of informing B with a message. What does the waiter do in the meantime? It just serves SMB because it's a promise. So it's a data structure sitting there waiting to be fulfilled, no logs taken anymore, and we can just continue serving other SMB requests while the lease is being broken. Okay, next level. We had to add yet another layer. As I said initially, TDB at its core is a shared hash table. And the API dbwrap fetch locked logs much more than it should log, because underneath it used TDB chain lock, locking a whole hash chain. And the problem now is that SMBD has to do expensive operations under a lock. So we take a lock, and one of these expensive operations is unlink. Unlink can take ages in some cluster file systems. Open can take ages. And even close, if running on an NFS file system, close can take ages because close is the moment when NFS clients flush their data. So this means we take a lock, we close a file under the lock, and it can take many seconds, if not minutes, until the close call comes back. And so during this time, the database is partially locked for the whole hash chain. Clustered Samba now has a special problem. So SMBD wants to open a file, it takes a full chain lock. Now the file system takes a break for some reason. It has to pull data from tape, or it has its own problems with cluster communications being delayed, blocked, or whatever. SMBD, having taken the chain lock, sit in the open call while the cluster file system is busy getting the inode data. Now ctdb finds out the node is in trouble and needs to get rid of the node. Getting rid of the node in the ctdb architecture means that it has to recover databases, which means that it has to walk the whole database on all nodes to really get the latest data of all records to all the nodes. However, the TDB file is partially blocked because Samba sits in open, which it can't really do anything about because it's a blocking syscall. So ctdb can't cleanly expel that node from the cluster because it really can't traverse the database getting the latest data from all records. And that in practice is actually a problem. That is essentially caused by TDB doing overlocking, TDB doing its locking while SMBD has to do expensive operations. What did we do? We implemented per record locks. And why did we do that? As I said, TDB was implemented, TDB was extended to, for example, do persistent TDB files. We store our workstation password when we are a member of an Active Directory in secrets.tdb. Our configuration is in registry.tdb, and that better be stable. So we implemented transactions for TDB, which are very, very coarse, I would say. We log everything, we do the transaction, we do our msync, fsync stuff, and then we unlock. So while we are doing this transaction, everything is stalled. Everything else is stalled. This needs to be extended to the cluster. However, there's a little problem. CTDB, the implementation of CTDB has no global state. So CTDB, the cluster TDB daemon, cannot do a global lock. So what did Samba do? We need a global lock that is valid across cluster nodes. And now Samba implements its own advisory locks on top of one of these databases that we have implemented forever. We call it glog TDB, global lock. How is it implemented? A global lock is implemented is represented by one record in this glock TDB. So what happens? It's an advisory lock. I want to grab a lock on glock TDB. What happens? The lock holder is entered as the PID in a record representing this lock. If somebody else also wants to take the lock, they notice, hey, somebody else has the lock, and they just wait using dbwrap watch for me to drop that lock. And yeah, to do these operations, just enter ourselves into this glock TDB for the global lock to tell others, hey, I have the lock. The chain lock in TDB are only held very, very briefly. In particular, we don't do any blocking operations like open, close, unlink under the TDB chain lock. All we do is we just take the lock, enter ourselves into a record, release the lock. Using this, what we now can do is we can do save TDB as ctdb transactions. We can just take a lock for the ctdb transaction, broadcast our changes that we want to do to every ctdb node, tell every ctdb node, hey, do your local transaction on the TDB, release the lock. This means ctdb transactions are now safe. Next requirement. Samba implemented in a cluster has to protect itself from having different versions. Samba's internal databases like logging.tdb and all the others are not versioned, not really. I mean, some of them have version strings or version numbers, but we don't really have bumped the version number. We don't have any compatibility code. So what this means is that if you have several daemons running on the same databases, you better make sure that they are all the same versions. And for this, the glock was extended to carry the version string. So how is this implemented? SMBD takes a shared lock on the central version record. It tries to upgrade this to an exclusive lock. If that's fine, it's an exclusive lock. We know that we are the first SMBD starting up in the cluster. We write our version. If we can't upgrade this shared lock, then we know somebody else has this exclusive lock. Somebody else exists in the cluster. We assume that the other one has written its version, so we compare the version and we just exit again when the version doesn't match. So now we have written our version, we downgrade to a shared lock again, and we allow others to join this way. And what we now did is we implement the logging.tdb on top of this glock. We have everything we need. We have record logs, we can take logs, and we can store data in such a glock. So this was initially implemented for just preventing the version mismatch, but it was reused to also store the logging.tdb data, just to get rid of this TDB overlocking. Which means that with this implementation, TDB is not locked anymore while SMBD sits in unlink. So now I have a few slides. I have a few minutes. I have a few slides. Our logging.tdb, so this is like a bit like an onion, and I'll skim over the slides and I'll come back to this one. So we have a logging.tdb payload, we have glock data, we have dbwrap watch data, and then we have ctdb data, but I don't have a slide for this. So we start with the logging.tdb payload. That's all that Samba initially stored in the TDB file called logging.tdb. What is it? We have metadata. That's a structure we call share mode data. What do we store there? It's like timestamps that can't be represented by Posix. It's information about whether the file has to be closed, has to be deleted when closed, and so on. So it's all the metadata that we can't really store in the inode, but which is needed for SMB operations. And that's just a uint32. That's NDR encoded, which means all our marshalling of complex structures is done with network data representation. Why is that? it sounds a bit weird that we use what Microsoft uses for MSRPC, but it's what we have a good parser. We have a very flexible parser and marshaller for NDR. So whenever we have a structure that we need to put on disk, that we need to put on a database, we use our PIDL Perl-based IDL compiler and make that into NDR, network data representation. So this is a complex structure that is NDR marshaled. Then the record holds a complete array share mode entry. And I've given a lot of talks about this. The share mode entry holds the information on the individual client and process opening the file. You find the share mode and lease information in this share mode entry, in any of these share mode entries. And in this case, we have N openers. And yeah, that's the logging.tdb payload. Next, we have this wrapped in glog data. If you look at this, we have a server ID. And as I said, server ID is our representation of a PID cluster-wide. So we have one field that says, hey, this is exclusively locked. And if it's not exclusively locked, the PID, I mean, the server ID contains the real Unix PID. If that is 0, that means this record is not exclusively locked. Then we have a sequence number. For this record, every change goes with the sequence number bump. And then we have a little array of a number of PIDs that have this record locked in shared mode. So if the record is exclusively locked, then essentially there can't be any shared lockers. The implementation, I believe, has that you can also enter yourself in the shared array, meaning, okay, I'm waiting for the exclusive lock to be dropped, and then I retry. And so as part of the payload in the glog record, the one that initially was just the version string for TDB, for clustered Samba, protecting against version mismatch, the payload in this glog record is now the logging.tdb data that I put up in the previous slide, this one. Essentially, that's a blob that we can put here. Glog, of course, is implemented, as I said, on top of dbwrap watch. And the structure dbwrap watch looks like this. It's the metadata that the dbwrap watch code puts on top. So that's simple. It's just an array of PIDs who want to inform if the glog payload changes. And that's about it. Wrapping up. So Samba implements SMB semantics using shared memory. We put in the dbwrap abstraction to extend this to a cluster, just to be able to flexibly not directly call the mmap-based calls, but to just implement function pointers redirecting this into a cluster. In particular for leases, and of course to implement the glog, we need to asynchronously monitor record changes, and we put this into an abstract API, dbwrap watch. Hides the complexity of explicitly waiting for leases to be broken. That's the initial use case that we had, but it's used in other places now as well. So per record logs are implemented in the glog code on top of this dbwrap watch. And if you look at the implementation, we have taken great care. If you look at all these layers, dbwrap watch, glog data, logging.tdb in the last one, the implementation, the simple implementation would be to just push it around using a lot of memcopy and so on. The implementation, and the records can get large. They can be up to like 0.5 MB or something, or even more. So using memcopy for all of these would be expensive. And we have actually seen this show up in profiles. So we took a lot of effort. We implemented all this to avoid memcopy wherever possible. You can't avoid it everywhere, at this point, but there's very few mem copies pushing around the logging.tdb data. So if now somebody else wanted to implement Samba logging on top of other key value stores, you can split up these layers like logging.tdb, dbwrap watch, glog, and so on at any point. And essentially, we are sitting on TDB, a simple key value store. Now with the glog, you could implement this without real per record logs. You have to implement, of course, some atomic operations that are implemented in glog at this point, but we don't really use global logs across multiple calls, across multiple blocking calls from the key value store, in this case TDB, in our case TDB. We don't use that anymore. And you can utilize this to implement the Samba logging on top of any key value stores with some extended semantics. Okay, if you have any questions, contact me under these addresses. I will be available.